Okay. Questions?
So we just started from first day, standard age.
Homework 5,
Uh,
stuff like what's it called? Like similar
13.
and
Yeah.
wait.
So just say, like if there's a slot. Yeah.
For stuff like the matrices stuff and like similar and like determinant and stuff. Will we need to know that for an exam?
No, not the matrix. I mean, you know, I don't know. I would consider it fair if I asked you something that you needed to draw on 3110 or something like that, but it's not going to be anything. I don't expect you to know singular value decomposition,
Okay.
but you should know that if you needed it, that the determinant of A B is the determinant of A to the determinant of B, something like that.
For I just have more like definition questions. For an R module, if both like Rx and XR make sense, but they map to different elements in M, would they be two separate R modules still? Like, would it be like a left and a right one?
Well, I mean, it's a left module if it's a left vacuum cleaner like that, and it's a right module if it's a right vacuum cleaner, right? Yeah, so what it means to be a module is okay, so it's an abelian group, right? Left means that for all R M, right? And it obeys the rules, right? That is. Uh, all right. That's a left module, and that's good. Yes. Now it's a right module. If all this is true on the other side, right? And it's a module if it's true on both sides, but there's no guarantee if the ring's not commutative, for example, that R times X is the same thing as X times R.
So if it's not commutative, then would it still be like two distinct left and right R modules?
Well,
because as long as it takes it into M, then it's
right.
just
So if you have M, so what you could do is uh, That's a right module. Now, if a module is both a left module and a right module, we say it's a module, but there's no guarantee that R times M and M times R are the
Okay.
same thing, right? But you would want that to be true if R was the identity, but of that. And of course, this is reserved for a lot of things. So for example, you can say it here. So if R so suppose we have n by n matrices over reals, right? So this n by n matrices. Then a good R module here is Rm, right? And this is a left module because the matrices multiply the vectors on the left, right? Because you have an n by n matrix and an n by one vector, right? So this is a left module, but the multiplication doesn't make sense on the other side, right? You would have to do the transpose.
Okay.
Like some element, let's say X in M. There's no guarantee that it's of the form Rm or some R and R negative X, right?
Yes, it is in the unitary case because it's a form one times X.
But if the R is not unitary, is there any guarantee that's
I don't see why.
otherwise there?
Or can you have an example? Or I don't know if you can like come up with one off the top of your head, but like showing something is an art algebra. Cause like, what is it like? I know like equipped with a homomorphism, like F from R to A. Like I know what that means, but like, can I just say this is an art algebra? Like, it has this homomorphism. Like, what is that homomorphism?
Well, so what happens is, okay. Is a ring. And you have these more into a homomorphism. And we emphasize here, I like my homomorphism. This is very good. And we know that P of R is contained in the center of A. And here, I think my blanket assumption was R was commuted from that to, right? But in R algebra, and this is the way I always remember this. I hope I remembered everything here in the definition. The way I remember this is the fact that this generalizes to matrix, right? And so, for example, if you have just for example, M2R. It's two matrices. Now, I think we can all agree today is a ring, you know, you multiply two by two matrices, that's what gives me out, so forth. The ring here is R. And this sort of corresponding with the identity here, so you have to take the identity to the identity, and you want phi of R to be in the center. Right? So what is this? So you take the number x to the diagonal matrix x 0, 0, x. Notice this is actually the scalar x times the identity matrix. So it's in the center of the ring. If you have any matrix will compute with both the scalar and the identity matrix. So this thing's and so that's the way I remember it. This mimics this situation here. But for example, there are much more general things. So if you have, let me just this is kind of a catch-all here. If R are commuted to ring 1, T is always an R algebra. And homomorphism is just a good thing. Right, if we realize R is a subgroup of T, this inclusion, and this does everything. I mean, it's almost a cheat, right? Because I demand that this ring homomorph, it takes 1 to the identity of T. And of course, the image of R is in the center because T is commuted, everything's the center. Right? But there are other things you can do. You can take R into, you could have, here's one that's got a little bit more oomph to it, but not much. So just take R, take the ring of polynomials over R in 2 non-commuting variables, right? So in other words, x, y, and y x would be considered 2 different things, right? So the variables don't commute. This ring is very non-commutative, but the map phi takes R to the constant polynomial R, and it's in the center of the ring, right? Because any constant commutes with all those.
Is the center of the ring multiplicative?
Yes, yeah. The center of a ring is a subring of a ring. Not necessarily an ideal. In fact, not usually an ideal, but a subring.
What's important about the definition is the fact that phi of R is in the center, because don't all ring homomorphisms take it like the identity to the identity?
Yes,
Okay.
well, I mean, it depends on who you talk to, but my default is that you take the identity to the other. That's right. And so actually, one of the theorems we proved beyond this is that any A algebra is an R module. So if you have A as an R algebra, it's an R module. So you can use that observation here to extend this. Phi of R should go to R times 1A. That's essentially how that works. Yes.
Could you write out, using set building notation, what the center of A is?
Yeah. And notice that, of course, 0 is in the center, the identity is in the center. And so at the very least, this is actually subring, but it's fairly easy to see that if X and Y are in the center, and so are their sum product. Right. So
What?
the center will at least contain the subring generated by 1.
Why is it for all R and not R and A?
Because I miswrote, you're absolutely right. Yes, thank you, it's for all R and A. Yes.
Why do we want it to be in the center of it?
Well, this is a community group identity, and part of the motivation, I don't really know how to answer that question because I'm not the one that made the definition. But it makes things work out, right? I mean, so for example, you've got, you've got this matrix ring and there's sort of a natural copy of the ring that sits in there as the diagonal matrices, right? And that's, and of course, this thing right here, yeah, R is a commutative ring. Yeah, that's our thing. So, it just makes things work nicely, right? You can go and have a van out where it's not in the center and see what you can get back, right? Yes.
You have a question on your 2013 exam that is something that might be applicable for us. You write that you have a short exact sequence of 3 vector spaces.
Uh-huh.
And
3 vector spaces, is that what you said?
yes, so 0 to V1, V2 to V3 to 0.
Uh-huh.
And then say to show the sequence splits.
Let's see. Oh. This is a short exact sequence of vector spaces. Over. Show the sequence splits?
Yes.
Any ideas? Over a field, all modules are free, they're all projective, they're all injective. Free is the obvious part because that's essentially what we find it. Projective because any free is projective. Injective is less obvious, right? I mean, you can, well, I'll talk about this in a moment. I think the easiest way to do it is to look at this. V3, because its vector space is free, right? So it's projective. So it's because remember, one equivalent characterization of projective is once it's tail end, if this is projected, the sequence has to split. Right, okay with that? And of course, as a consequence of that, we see that frees, in this case, over a field, the frees are also injected. Yes.
Could you show that the projected means that the sequence splits again?
Oh, yeah. He is projected. And this is onto it. All right. So I'm going to put P up here, and this is the identity function. Because of the fact that P is projected, there's an H that goes back. So in particular, when I do H, then I do G, this is the identical P. And that's what it means to split. So it's also true over a field any module is free, any module is rejected, any module is injected. Why is this true over a field? You can do something direct, it's a little bit harder, but why does injective imply free? In a very silly way, injective implies free over a field. Because given an injective module over a field, it is free, right? Because any module over a field is free. So the injective is just almost not even needed. Every module is free, so certainly injective applies free. Everybody agree with that? Why do we get the injective property? Well, here's one way to do it. Assume why, in other words, why is it true that free applies injective? Well, so suppose that you have this exact sequence. This one's projective, so the sequence splits, so you get that. So this is projected, but you can do it this way as well. Maybe I'll this is we need to build H. Now let's suppose that we're over a field. Any ideas on how we might do that? Well, I don't know much, but I know that since I'm over a field, every single one of those guys, A, B, and I, they all are free. So they all have bases, right? So here's a way to do it. We want to define H. B to I, right? Such that we call some. When I do F and then I do H, same thing. Okay, so how would I do this? What I would do is, of course, the image of F is a submodule of subspace, if you will. Right. So let X be a basis. All right, I'm going to use this basis. Actually, I need something bigger. So I need this H to be defined on all D. Expand X to so take my basis for F of A and grow it to a bigger basis for all of the. Everybody okay? Now, all we have to do to determine H is to tell it where the basis goes, right? So On basis. Yeah. One thing. Read this basis element. If it's in the original X, the basis of FA, what should I do to it? Good. So send it where the vertical G was going to sit. Right, so send that basis element there. And what if it's not there?
You need to be interested. Like big X is the basis for B, so it's all instead of B.
Yeah, I mean, I could use better notation, but I consider this to be the inclusion at basis of so.
Sure.
So yeah, you're right. I mean, what that really is X is there's a unique preimage back in A. And it is unique because F is 1 to 1. And what if not? Well, X is in X half, but not an X. Yeah, send it to 0. That's the easiest. Actually, you can send it anywhere you want. Right? As long as you can see, you can just make up random practice. It's still gonna work, right? But send it to 0 is the easiest thing to do. And now what happens is if you start here, start with some basis element this, then it goes here and goes to the same place here. So it's going to, this composition agrees on the basis elements. So that's one way that you can do it, sort of. I don't think I would recommend this really, but you can certainly do it. And it depends very heavily on the fact that these are all have bases, that these are all free, that these actually the over field. Because in general, over a ring is not a field. For example, the integers, free modules are free modules are pretty far from being objective in general.
So the fact that it's a free module, the fact that it's a vector space gives it free.
That's
But
right,
usually
because
modules
all of
aren't.
these animals up here had to be vector space. They all had to be free. They've all got bases, and in all cases, they kind of came off there.
So if it's just a random R module over a field, it's not necessarily.
No, any R mod, if your ring is a field, if your ring is a field and you have a module, it's automatically vector space.
Okay.
And just because it's free over some random ring doesn't mean it has some of these types of problems. Yes.
Could you show that being over a field implies free? Like being an R module over a field.
That's one of the homework problems, right? No,
Don't remember.
I think, isn't that a homework problem that, how does it go? I ask you guys that homework problem? I'm pretty sure it is. Let me get it and we'll talk about that one. Sunglasses.
It's on this, we're gonna do this next week.
Oh, look at that. So it's free if and only if positive field. That's what you say. Every art module is free. If and only that. one of these directions and decide it would be easier, which one. That's right. If R is a field, we already know from the class, if R is a field, then any module's vector space has basis, so if everything's free. Right? What about the other direction? Suppose every R module is free. What does it have to be a field?
A vector space, like the only difference between a module and a vector space is like that a module is over R. Well, every vector space is a module, but a vector space is over X.
That's right. Vector space means it's over division. Right?
Then it
Or
automatically
field.
basis, because it's vector space.
Yeah, well, any free module has a basis, right? Okay. What about the other way? So, and now suppose we have the situation where you got some ring, you need to bring that in, so every R module is free. What is this? Maybe become positive. Suppose that you have a community variable identity that is not a field. What sets? I'll give you an example. Z. Z is about the best community variable identity subfield that I can think of. What do the free modules over Z look like? Direct sum, a bunch of copies of Z, right? Give me an example of a Z module that's not free.
Wait,
That is correct. Q is not free. Somebody give me another example. Q is a great example. It's going to be hard to work with in this context.
Oh, Z2.
Oh, that's a great example. Z2. Because any abelian group will work. And Z2 is sort of, what's wrong with Z2?
Can't create it as the direct sum.
Right, that's right. But it can't have a basis either way.
Oh, yeah. Because you can't form a linear.
How do you get C2 from Z? What is true about what makes a field different than your garden variety community range? Nothing. Everything has an inverse. Okay, that's the right track of what I was looking for. Every commutative ring with identity has what? Big pair of any commutative ring with identity has some kind of ideal, a maximal ideal, right? A commutative ring with identity is a field if and only a blank is a maximal ideal. What's the maximal ideal in the field? What sets apart a ring that is not a field is it has a non-zero ideal. So if R not then there is a non-zero ideal. R mod I is an R mod. That is a general statement that I can make for any community identity. Any R mod I is an R module. Multiply take an element R and R, multiply the coset X plus I by that, you get the coset X, RX plus I. Right?
And also trivial.
I is not a ring. Because it doesn't have an identity.
Is it ID?
I is an ideal, but I want my modules to be unitary. I didn't have an ideal.
Oh.
This thing, since I is not zero, this can never, ever be a free R module. But see what? I'll give you a little kick down the road. If this were a free module, we would have to have a basis, right? And what's a basis? It's a linearly independent subset that spans, right? There is no one element set in here that's linearly. Every element of this R mod I is linearly dependent. I said what?
Every of R mod I,
I claim this element, whatever element you pick out of there is linearly dependent.
You multiply it, maybe be non-zero.
There we go. It's important that I want the idea is not zero. Pick any element that is non-zero in I and multiply alpha times R plus I. And what do you get? You get R alpha plus I, but R alpha is in I, so that's the 0 point. So it's impossible. The existence of a non-zero ideal means that you can always create a module that's not free. And that was the first example, the Z2 example. Does that make sense? Right, so there's no linearly independent, there's no linearly independent element, so you can't possibly have a linearly independent subset.
how, wait, can you repeat how there's nothing? Like, what is the zero not for how?
Well, so just suppose that this is an arbitrary element.
Mhm.
Suppose it's linearly independent. Right, but notice if I multiply this by alpha, alpha is not zero because it's a non-zero element of I.
Mhm.
And if I multiply by this, I get alpha R plus I,
Which is, oh, which is in.
which is 0 plus I. So,
Okay,
Okay. Other questions? Yes.
Will we need anything from like group theory for this exam specifically? Like something like specific to group theory, like CL theorems, we wouldn't need something like that.
Are you asking for permission to get all about that stuff? I mean, I haven't figured out a way to put CeeLo theory yet, but if you want to go home and try to figure out a way, I'm going to do it. So. Yes.
In general, these modules are easy.
I'm sorry, run that by me again.
In general, modules are finite or no infinite.
Well, I mean, I walked up to one on the street, I expect They certainly don't have to.
Okay.
For the direct product, in class you added elements of the direct product. And it was like AI plus BI equals AI plus BI, and then like,
Mhm.
so are you just like that's AI plus BI will now correspond to the first element?
Yeah, so like, it's sort of like this, so. So this is the rule where I talked about. So you have these two sort of, nets. That's what they look this is to do. Big generalized sequencer net, they're gonna call it. Right?
Mhm.
That's a little like that. This is, let me show you this to you. A1, A2, A3. That's all that's going on here. It's just there might be just a whole buttload of these coordinates that I can't even, maybe I can't even list them sequentially.
And if you have like, if eyes, are the eyes, the indexing sets have to be
Yeah.
equal?
Oh, yeah.
Okay.
Yeah, I want the indexing sets to be equal, so I'm in a single direct product or direct sum, whatever I'm doing. And the indexing set is just over my family of modules. Okay, other questions? Yes.
In terms of the, uh, diagram chases that we've done, what would be, the most important one for us to know? Because some of them felt a little arbitrary. That it just in terms of like showing how to do diagram chase as opposed to something used for proofs.
No, I mean, so the stuff that I proved for using a diagram chase, through the short file. Those two are tools unto themselves that are used later. Diagram chase was a technique that you should be familiar with, that I use to show particular things, right? The good thing about the diagram chase is there's only so many things that, because there's only so many directions to go, right? And so we can try everything. It's almost like, if you're doing, you know, where you're doing intervals to calc too, right? There's only so many things to try. Others.
For the snake lemma, I know like what the co-kernel is, but like, is that like, how does the kernel of G3 take it to the co-kernel of G, or like, how does the, I don't know what that's, how does that map? Like, what is that? How does that map?
No, I'll show you. Here, let's see. So you have. This implementation. So what we have is that sequence was her G1, her three, and then we snake it. Co-curve, G1. Co-curve, 2. And here. Here, this is basically F1. It's just restricted down to the kernel of G1. Step 2, and these are induced by H as well. Now the question is how did we go here? Now remember, you have the kernel of G3, co-kernel G1, and the co-kernel of G1 is B1 image right. So the question is how does the snake thing work? Well, you start, say A3 here. Right. And what do you know about A3? It's in the kernel of this, so it's down to 0 here. Agree? Now, because of the fact that this is onto, there's an A2 here that goes here. Now, it's a little bit concerning because this choice is not unique, probably, because it's on. Nonetheless, we push forward, and A2 goes down to B2 here, which must go to 0 here. So I made this flaky choice because this could be a bunch of different things. But nonetheless, I go down here and I notice wherever this goes, no matter what my choice is, it has to go to 0 here. But the exactness here gives a B1 here. Okay. Now, this B1 actually, it turns out it's not well defined, but it is well defined modulo. That is, given two choices that I make here, they vary here by something in the image of G1. And so the B1 we get, we actually go to B1 because, and I can give more detail if you request it, but when you go back here, you make a choice. The choice might not be unique. So you go perhaps to do different things down here, but both of those things go to 0, which means they both have pullbacks here. So there's two different things that you got, B1 or B1 prime. And so your choice here isn't unique, but it turns out that B1 minus B1 prime, your other choice, vary by an element of the image of G1. So the difference between them has to be something in the image of G1, which means even though they might not be the same, they define the same coset here. So that's why you go to this quotient and not just be opposite. Right. So that's, sometimes people even write this, so write, A3 inverse composed of G2, H1 inverse, right? By the way, notice once you pick this B2, choice back here is unique because this is 1-to-1. The problem is you might have two different, depending on which choice here, you might have two different things. But anything that varies by difference about something. In one. Yes.
How do we know that B1 prime, two different choice? How do we know that they vary by something in G1?
Like
Image of here. What's that?
right? So for example, so you make a different choice down there. So you get something different down here. Get something different here, right? Of course, by the time, so you and I make different choices here, but once we've done that, my B2 and your B2 prime are uniquely determined once we make our choice here. And then what they pull back to are uniquely determined because H1 is 1. Right. Now, if you notice A2 minus A2 prime both go to A3, so there's something here that goes to it. So there's an X here that goes to A2 minus A2 prime. Right?
Yes, because
A2 minus A2 prime is in the kernel of this map.
yeah, so it'll be the image.
Right. So that means where does this X go? Well, this way, this goes to B2 minus B2 prime. So here, so if you go this way, it goes to B2 minus B2 prime. Right? That means that it goes here, something that goes to B2 minus B2 prime, which equals B1 minus B1 prime.
Because of what?
Because this is one sure this way. And so, right, in particular, what you get is what we call this G1X. Right? So that means that B1 is B1 prime plus G1 of X, therefore, which is, well, let me write it this way. Therefore, cosine B1 plus G1 is equal to B1 prime plus G. So it's well defined. And it's painful, but I mean, you know, you probably should be careful and show that it's not multiple morphisms, et cetera. Sure. It's not terribly difficult, but it's like sitting in this chair. Questions on that?
For theorem 12.4.8, when we say like we divide the diagram like 0, A, B, C, 0, and then like create our module homomorphisms coming down to like 0, A, direct sum A plus C, and then C0. Is this is called a split exact sequence? Is it the top row or bottom row that's a split exact? The bottom row?
Let me take a look at that. Which one is this theorem 12.4.8? Well, so what the theorem says is if you have that short exact sequence in the beginning of the theorem, then all three of those conditions are equivalent. So if you've got one condition, you've got them all. And if you've got one, hence all those conditions, then the sequence is called split exact.
Oh, so it's like the A, B, C, and 0,
That's right. What it means to
Okay.
be split exact is there's a function that goes back from C to B that composes the identity, or one that goes from B to A that composes the identity. And the third one is the one about how the sequence is isomorphic to that particular split sequence that I gave.
When we talk about home R, like as at least in 12.7, we have the map from home R AD to home R CD. So the input is a function, is a homomorphism from A to B.
Okay, so I'm sorry, so where are we?
12.7. It was like the intro or like the that part, like the very beginning of 12.7. I don't know what the symbol is, but N from home R AD to home R CD.
Oh, right.
So the input is like a homomorphism from A to B. And then that's taken to a homomorphism in CD.
That's right.
But then what do you how do you evaluate the input?
So you would take an input.
Mhm.
Well, on the left side, you just put your input. Where the heck is that? Okay, you would just put your input A into F and go with it, and just be F of A. On the other side, what would happen is you would put your input into gamma,
Mhm.
gamma of A. Now that's gamma of A is going to give you something. Right. So on the left side, you just put A into F. On the right side, that homomorphism, that jumble, the tornado F gamma, that's a homomorphism from C to D. So you would put a C in, then gamma of C is something in A. So gamma C is now something in A. Evaluate F that, right? Now F of gamma of C is something in B. And now that big fat thing in B, you put that in tornado, and tornado takes it on to D.
Okay, so is the input isn't a function, the input is a
The input is just, yeah, so the input is just something from the domain, right? So
Okay.
your first homomorphism goes from the domain A to the target B. And your second one goes from the domain C to the target D.
okay.
And it does it by function composition. Yes,
Divisible groups are just, injective groups for Z modules? Like, is that the best way to understand this?
for a Z module, a Z module, which is of course a Z module is injective if and only if it's divisible as.
What do you mean by every R module embedded in an injective R module? Like what does embedded mean?
To be embedded is, there's a couple ways to think of it. You can think of M as a submodule, an
Okay.
injective module. More fancy way to think of it is there's a one-to-one function from M into a one-to-one, I should say, R module homomorphism from M into an injective R module.
Unless otherwise stated, I think we assume that the module should be compared.
Yes. Yeah, I'll let you know. To be something good. And of course, because of your question earlier, before, now know. I guess that there's a reason why we want to focus on unitary modules, because if they're not, you break it up into a unitary piece, 3 has 1, and a piece that's basically the 0 module, or the trivial module, I should say.
How would you recommend studying this exam?
Not extensively. I know the definitions and stuff. Right? Make sure that you got those cold. And I put 40 points with proofs on there, but I don't think it's too bad. I certainly don't think I don't think it'll be too difficult to collect points. You know. Yeah, don't, make sure you're rested, right? So don't stay up all night till 3 in the morning, some crazy crap like that. What else was in? Yeah, my default for a ring is I'll make it clear, but I don't want it to be confusing, but.
So this is just like every R module is a homomorphic image of a free module, and that's because there's the function x to f, and then you can create a function f bar from f to m such that f bar iota equals f.
Right, and
Okay.
essentially what that is, that's setting up a basis. And the reason that works is because when you have a free module, everything can be written as a linear combination of that basis uniquely. And that's what allows that function to be well defined.
And then we have every R module is a homomorphic image of a projective R module. Like, why is
That's a silly observation,
Mhm.
because it's dorky, because every module is the homomorphic image of the free module. And
and
any
every
free
module-
is projective, so you could just say, oh, look, I can make it a homomorphic of a projective module just by taking that projective module to be free.
What makes a diagram? Like, I know what a commutative diagram is, but like, what makes it? Like, how do you prove that a diagram? Or like, you just show that it maps to the
Well,
same element?
okay, so usually what you've seen is where I'll say, okay, look, the diagram is commutative, which
Mhm.
means it doesn't matter which way you go, same answer. If I just gave you a diagram with a bunch of maps that said prove it's commutative,
Mhm.
you'd have to go through a test that it works, right?
Okay.
Like if you start here and go here, it's the same thing as going here, you'd have to test that out.
So for the injective and projective diagrams, are those commutative?
Yes, yeah,
Those
that's
are
right.
commutative.
Yeah, and that's the point when you that's another way to put it, like with a projected one, for example. So what you do is you get something in, what is it, F? Is it equal to- That means that diagram is going this way, it's the same thing as dropping down.
And for showing something is exact, you only really need to show that the image is contained in, or the image and the kernel. The image of a function is equal to the kernel of the next function. But then to show that it's like exact in terms of like 0, A, B, C, 0, you have to show that like the first one is 1 to 1 and the second one is on 2.
Right, but really, you're just doing the same thing, right? Because, what I mean by that is. Now, I think you're capturing the exact, no, the image of F is equal to kernel. G, but you're doing the exact same thing here because the image of this is 0.
Mhm.
And the kernel of this, you're having to show, to show that this is 1 to 1, it's equivalent to showing that the kernel of 0, which is the image of this. And it's the same thing here. The image of this, you're trying to show here, the image of this is the kernel of this. The kernel of this is everything. So it's all the same.
So if it wasn't 0 on the endpoint, you wouldn't have to show Or,
Right, so if I said. So if I give you something like this. And said. So it's customary, although I'm not gonna try to trick you and we'll, you know. Fill any questions you have, if I asked you to show that this was exact. You almost sort of ignore the H, so if I said, show this is exact. You need to show exact here, here, and here.
okay,
That's it.
Yeah.
given a diagram like that, it's not necessarily, like, you can't conclude that F1 and or F1 is 1 to 1 and F4 is on 2. It's like the 0 that makes it special.
In
Okay.
fact, when you use these kind of tools to do computation in algebra, there's sometimes things generated called long exact sequences. They go on forever and they're always exact. And usually they're periodic, so you can figure out, it's spliced together by these sort of similar things, but. Yeah, there's no reason to suspect that this is 1 to 1. It might be, might not. Yes,
If you have 0 to A to B to 0, and that's an exact sequence, the function in the middle by different.
yes.
You always have GF equals sigma.
Yeah, if it's exact, because, wait a minute. This is equivalent to saying the image of that is contained in the kernel. Right, because all the junk that goes here gets pushed on 0, so it means the image of this is in the kernel. Right, so, that's actually a more general statement. Do you remember when we talked about complexes? Right, and a complex means that when you compose any 2 in a row, you get 0, right? So this is a special case of a complex, but it's even better. It's exact sequence.
So you always have that.
Yes, so for a complex, what happens is any 2 in a row are 0, which means the kernel of any, or the image of any map is contained in the kernel of the next. But in a complex, the kernel here might be much bigger than the image. Yeah, one silly way to make a complex is just put a string of A's, A1, A2, A3 forever, and put the 0 map between every successive one. That would be a complex, sir. Did anybody ever see differential geometry? I was reading something the other day and I thought, so here's an application. If you take the differential of an inform twice, as well, yeah, we can restrict ourselves to 3 space, but it's a more general. So if we take the differential of an inform twice, then as long as the functions involved have continuous second partial derivatives, doing the derivative of the endpoint twice gives you 0 always. Do you remember in Calc 3 probably? Did you ever look at like potential functions? Right? So these potential functions, so you'd have something that was the gradient of potential function, and then you could do like an interval around a closed loop and get 0, right? That's this stuff. It's the kernel, it's exact sequences. That's essentially what's going on. I can recommend a good book, you can still read about this, but you can see this kind of an action. It doesn't talk about the alpha a lot, but you can see it. I forget exactly the name of it, but it's by Stephen Weintraub. Weintraub. Last name Weintraub. Look that up, make sure I got that right. Sure I do. Yeah. Yeah, that's right, because that's right, they make it complex, and the ones that are good are the ones where they call, in fact, I think they call the forms exact, so they call something exact. A form exact if it's the derivative of another form, so that's like, you know, and so that's where they're trying to get the kernel inside the image, so to speak.
Would it be moduli spaces of unit search?
Yeah, no, it's more on the, it's.
Differential forms theory of practice.
Oh, let's see, I think that's it.
Is it take on?
Yeah, he came there after I left, but I knew him a little bit.
Like from 2014, second edition.
Yeah, I think that's, I enjoy it, but. So, so this stuff comes up, you know, it's interesting because we're measuring this stuff that I think Green's theorem, stuff like that you learn become great, so.
What's all fair games?
Oh, yeah, so. Yeah, you should know the definitions of the harm, that's how it's done, right? I'm not gonna get too much into the weeds, but you should know. You know, kind of the definitions of the harm, so.
Definitions of like home, or like,
Yeah, what it is. I mean, can you tell me what it is? Can you tell me, you know, how the induced map works, right? So, and it's just function composition.
for theorem 12.5.5, every non-zero vector space over a field has a maximum linear independent set.
Right.
Or a basis, not necessarily unique. Does like not necessarily unique mean that like the basis is not unique for that, like the vector space could have multiple pieces?
Most certainly.
But then if it's maximum, like for maximal ideals, it's either equal to the vector space or it's equal to the ideal. But like, what
Oh, it just means it's big. So what it means to be a maximal linearly independent set is if you have any set that properly contains it is no longer linearly independent. Right. I'll give you a simple example. Those two vectors are R2. Maximal linearly independent set. I don't care what third vector you try to put there, it's linearly independent. It's a combination. And this is the only basis. There's a basis.
wait, what is this a basis for?
R2.
R2.
Well, it's just like linear. This one, very good basis. This one, well, kind of sucks a little bit more, right? But these are like two linearly independent. And that these are both maximal linearly independent sets, right?
Oh, so like it can't contain that. Okay.
That's right. So that's right. If I had a third vector to this, I guarantee you it makes a linearly dependent set.
And when you say like expand a base, like a basis, what is like how do you expand? You just
So-
add an element to that.
So for example. This is linearly independent set. Right, but it's not a basis because it's not maximally set. I can add to this. How about this? And now this will be actually. Let me put her underneath this. Just make sure that one works, but. Because if I put these three vectors in a matrix, top row, middle row, bottom row, determines one. So this is what we said. This one's not maximal, so it's not basis, but I can expand this to a basis. And in fact, if you have any linearly independent subset of vector space, here it is. If it's already maximal, it already spans vector space, then you're done. If not, you can expand it. That is, you can find a basis that contains your original set with perhaps some other elements that form a basis. And that's what that Zorn's lemma thing did for us, because in our proof, we started with a linearly independent set and showed that it was contained in a maximum. Other questions?
So is generating kind of the same as maximal for bases? Like, when you say, like, in 12.5.2, we define like a basis as linearly independent generating set. And then we kind of like then we say it's like maximal and linearly.
Well, so a generating set is just a set that generates whatever module vector space is. Doesn't have to be linearly independent. And in fact, if I have any R module M, just take everything in M, and that's a generating set. Incredibly inefficient, but it works, right? That's a generating set. A linearly independent set. What happens when you have a linearly independent set is whenever you can write something as a linear combination of that linearly independent set, there's only one way to do it. Right? And that's so generating set gives you span. Linearly independent gives you uniqueness of representation. So when you can put those together, when you can have a linearly independent set that's actually a generating set or actually spans it, then you've got a basis. And now everything in your module, everything in your module can be written uniquely as a linear combination of the elements in this maximal linearly independent set.
So if we were showing that a substance basis, will we need to show that it's linearly independent and generates it, or should we show that it's max?
Oh, I would usually show that it's linearly independent and it generates. That is, anything in there is a linear combination of that. Showing it's maximal in arbitrary cases is probably harder. Now, if you've got more information showing it's maximal, it can be easier, right? So for example, if you have a linearly independent set of three vectors and you know you're on R3, then you can say, hey, that's got to be maximal because I'm in R3 and be done with it instead of going through the. But if you're not in that specific situation where you've got that extra information, you're probably best to show that everything's linear combination on the basis. Yes.
If you have a cyclic art module, is that isomorphic to some ring? Or
So it's cyclic R module.
yeah, is
And
that isomorphic to R mod idea?
well, see. So, but this means that M correct? Correct. So the answer is yes. See what it did here?
For us, we're saying zero.
So,
Yeah, really zero. Zero. Big product of the pyramid.
define phi from R to Rx. Right, so basically this is induced by the math that takes one to X.
So cyclic modules are free,
Not necessarily,
because you don't have the bijection variable.
that's right. Yeah, so we'll see what happens. So phi of R equals Rx, correct? Do I have to convince you this is an R module? It's okay. Okay. Notice that these is empty. Right? Because by definition, everything in Rx is form little r times little x, and so there you go. Right? So we have nice morphism from R on kernel of phi, isomorphic to R x. And the kernel of phi is an ideal of R. So the answer is yes. And in fact, this is free if and only if kernel phi is trivial. Other questions?
The kernel fee is trivial when n is infinite,
What's that?
when n is infinite. Or assuming you basically just never want to multiply by something.
I don't think it is it. It's gonna get you, say, kernel phi is trivial if, see, what's the kernel phi is trivial if X is not torsion. Right, so in the sense that kernel phi is trivial when Rx, R times X equals 0, applies R equals 0. Which again, that's the condition that you need for X to be a basis of that module. Okay, other questions? Where are your shoes? My shoes?
Yeah, they look nice.
Really? You've got me. It can't possibly be serious.
I
Have to rent that.
You like my shoes, huh? Oh, tell my wife that, I'm sure she got it for me, so. I get those $7 specials at Walmart, so.
You trying to get.
It's not working, obviously my ego is not attached to my dressing habits.
Well, tell us more about factorization.
Oh. By the way, I think that's a pretty sharp shirt. I think that, the Dark Side of the Moon is one of those iconic covers, and I think that was totally underrated. It's a great album, quite depressing, but very good nonetheless. Okay. Well, it's understanding. You know,
I went through revolves. I sent it to the University of Oregon. As I hit
You put
submit,
that on recording, by the way.
as I hit submit, look at it.
So you said the University of Oregon. That is awesome. I would love to be a fly on the wall for that.
It was like a 40 slip too, because I would.
You should have followed that up with, because after you did that, you had to follow that up with an email. It's like, oh, I'm so sorry, please don't tell the people at Oregon, you're my safety school, something like that.
You wanna explain why it's a free?
Oh, I would rather go to Oregon.
Oh.
Oh,
I'd rather go with this.
I went to Cornell, you're not gonna get any argument there.
So the tuition. What is the tuition?
Well, it's like always talk about that, but what it needs to be torn.
It's usually fine.
Yes,
not-
so. And. There exists a non-single R element such that R things. So this is the analog. So suppose that R is C, so suppose you become C modules deal with groups. So it's a torsion element if n times x equals 0. So that's an element of finite order. So for a general module, this is the analog of some a certain sense. And right. And notice this is kind of interesting. If you have x and y marked equals, then there exists a non-zero R S and R with R X 0 and S Y 0. Now, the question is x plus y also? Not always. So here's the easiest way. So can you find something that multiplies x plus y and you can see right?
RX.
Right. Basically.
So as long as RX is not two.
That's right. So the answer is yes, if R is if R is an interval domain, then the set of torsion elements actually form a submodule. Just like in the Euclidean group, well, of course, he is an interval domain. They're in a group. The elements of finite order within a subgroup in the Euclidean group. C6 as a Z module. All elements of order. six has C module. Z6 is C6 module. Not all elements are flourishing. Right, the ones that are torsion are. I can multiply by 1 bar, I can multiply by 3 bar, 2 bar, 3 bar, and it's 0. But if I want to multiply 1 bar by something, it's 0 bar. My only choice is to multiply by 0. It's a C6 bar. Right. But see here, the elements that are torsion don't form even a subgroup because it's not closed under addition. 3 bar is torsion, 4 bar is torsion, but their sum is 1 bar, which is not torsion. Yes.
We had something where the module M is isomorphic to the sum of the three module and origin, or is it a trivial?
No, it's torsion. And we're gonna talk about that when we do modules over together.
Is that the same as, is that just a generalization of result period? Or we
Yes, yeah. In fact, what we did from group theory, that decomposition, you remember doing that.
Yeah.
Find the elementary divisor, find the invariant factor decomposition. What you really need there is not the integers, you just need principal ideal domain, and you're good to go. So that basically, all that stuff we did is exactly the same, as long as you have principal ideal domain.
We can't say that an R module is a homomorphic image of an injective module.
Well, you probably can, but we'd be wrong. So for example, let me give you a good example. Right.
Oh, never mind, the arrows are going the wrong way.
Right, right. So, no, and that's actually, and that's one of the things is what you can say is you put a module inside the objective function. But see, actually, probably my guess is, so I'll have to cogitate this, but I bet you will find, I bet, I don't know this, so check me and I'll check me, is C as a Z module, so it's Billion group. I suspect that's not the homomorphic image of injective.
Could you say that in
Oh,
injective?
right, no, of course it's not, and I'll tell you why. Yeah, Z can't possibly be the homomorphic image of an injective, because if it was an injective Z module is a divisible abelian group, right? So Z is now the homomorphic image of the divisible group. We've proven the homework that any homomorphic image of the divisible group is divisible. Z is not divisible, so it can't be. Yeah.
Could you say that an injective R module is the home is wait that an injective R module is a homomorphic image of any R module?
Not of any, it's certainly a homomorphic image of a free module.
Okay.
Yes. If you have, can you have Z as a Z2 module? Yeah. So you're,
Any Z2 module is a vector space.
Right.
Z2 is a field. And so any Z2 module will be a direct sum of some number of constants. In particular, every element as a group will have order 2. And so No Z there. Right, you can't reverse it, right? Z2 is certainly a Z module, but Z2 is also a ring, and the converse doctor, Z is not a Z2.
What is the smallest ring, smallest in terms of cardinality that makes C that ring on
So you want the smallest cardinality of the ring. Which Z is a module over that thing?
yes. Is it?
I'm sure Z.
Yeah.
Well. I mean, if the module has unitary. Right. Fine. Yeah. Can't do it. Fine. Not the module's unitary. And if you remove the condition the module's unitary, then even if something stupid, Z's an abelian group, so you can make it trivially a module over Z2 by just making the operation take everything to zero. Right.
Well, we need to use eigenvectors and eigenvalues.
I doubt it.
As in the fake was.
I'm really curious about it.
Everybody in the room was thinking.
Most times by eigenvalues, I think.
She asked the question in the room, but doesn't think they hashed it.
Actually, yeah, no, actually, those last couple problems that I put on this last homework were really designed to kind of get you a little bit juiced up for the linear algebra, this module stuff. So it's, I really view that as something that's beyond the first exam, so.
Yeah, there's many brains.
Yeah, I mean, let's see what we get. I think
It's on the tip of everyone's.
products. But I want to go fast, but I'm just gonna give an overview of it, and then we'll do lots of PID.
Yeah, there's all the.
That's all I know.
The, like the matrix times the vector and the times.
I know there's.
You're not gonna give the. Just saying, letters. You're not gonna give the cliché as a homework problem, right? Please don't.
I give you one that you can solve, right? I mean, so in a certain sense, so if you have an irreducible quintic polynomial, there are 5 possible Galois logarithms, there's S5, A5, Frobenius group 4 to 20. The dihedral group on the Pentagon, cyclic 45. Three out of those five are solved in multiple. Now, if you pick a polynomial over a monopolynomial integer, if it's random, the odds are the Galois group is going to be S5. So,
And that's unsolved.
yeah, and S5 and A5, they're not solvable. So. Any other questions? No question now.